Let's take the graph of a function. So here's my xy plane. I'll draw my graph, and it's a graph of a function, so it passes the vertical line test, maybe like so. And there's two different ways I could describe that function. I could describe points in that function as a relationship of the x and the y values, and that would be saying that y is a function of x. But I could also describe it parametrically. Suppose that we have this t value, and when plugged into some parametric equations for x and y, we get the points x of t, y of t, which describe this same point. So we get a pair of functions, the parametric equations, x in terms of t and y in terms of t. And again, we're assuming that these describe the same curve. All right. So we can investigate this relationship by just considering, okay, we have this y value here. That y value, y of t, could be obtained in two ways. You could just plug in the t value, or you could take the fact that since y is a function of x, you could take y as a function of x, and where that x value is given to you by the parametric equation x of t. And I write it like this because assuming that all the functions here are sufficiently nice, such as continuous and differentiable and all that good stuff, then the chain rule applies. And on the left here, if I take the derivative with respect to t, and on the right, I do the same. Then I see that, well, y is a function of t, take the derivative, that gives me the derivative of y with respect to t. On the right-hand side, I can apply the chain rule. I want the derivative of y with an intermediate function x, so I'll take the derivative of the outside of the inside multiplied by the derivative of the inside. And perhaps a cleaner way of writing this is dy dt equals, here I want the derivative of y with respect to x, dy dx. Here I just have the derivative of x with respect to t. And you can easily memorize this because it just sort of looks like a fraction. Dy dt equals dy dt. And that's why we write derivatives like this, because of the chain rule. Anyway, this is just the chain rule applied to a curve, y as a function of x, which is also described by some parametric equations. And what's important is that dy dx is valuable because it gives us the slope of a tangent line. And this formula will allow us to solve questions about tangent lines, even if all we have are y as a function of t and x as a function of t. We just have parametric equations. All right, so let's take a look at an example of such a problem. So move this down here. I'm going to find the line tangent to the curve parameterized by these two parametric equations at the point 1, root 2. And we can see how we would really rather avoid getting y in terms of x. We could try that. Here we know that t is the inverse tangent of x, and we could plug that in for y equals secant of the inverse tangent of x. Now this does simplify, but we don't want to do all that extra work to figure out what the heck that would simplify to. So, we could also just take the derivative, but that would involve a chain rule. It'd be kind of gross. We'd rather just avoid that. So let's do that. Let's not go down that path. So instead, we're going to take advantage of this formula up here and use that to find the tangent line, because this tells me the slope of the tangent line. In the background, you would, if you did some work by plotting some tx and y values between negative pi over 2 and pi over 2, you would get this rough picture. Like so. And you can plug in some values of t that you know from the unit circle, the values of tangent and secant, to verify this. And so here's the point 1 comma root 2. So if we drew a picture, we know that the tangent line should be, since it's going upwards, it should be positive, but it's not exactly clear what that value should be precisely. And so this will allow us to, without even knowing what this picture is or these t values are, this will allow us to figure that out. All right, so let's actually solve the problem. So I will take dy dt. Let me figure out, actually let's start with dx dt. Here's my x. Since x is equal to tangent, my dx dt is equal to secant squared. And since my y is secant, my dy dt is equal to secant t tangent t. Okay, so now I want to know what the value of x dx dt and dy dt are at this point. And well, I need to know what the t value is for that point. And I can figure that out. I got x is equal to tangent of t. So x is equal to tangent of t. That would equal 1. All right, and so I need to know the value of t that makes tangent 1 between negative pi over 2 and pi over 2, and that's pi over 4. So I'll take that pi over 4 and plug that in to both of these and I'm bad at secant and tangents, so I can just go ahead and plug in to cosine and sine. So I have secant is 1 over cosine pi over 4, and then tangent of pi over 4 is of course 1. We just figured that out. All right, so here 1 over, that's going to be root 2 over 2, so that's square root of 2 squared, which is 2. Here, of course, that 1 goes away. That just gets me the square root of 2. So let's put it all together using our formula. Dy dt equals dy dx, dx dt. And now we'll just plug in our numbers. Dy dt is root 2 equals dy dx times dx dt is 2 at this particular point. All right, so dy dx is root 2 over 2. All right, so that's great. Now we have the slope of the tangent line. And to get the equation, all I need is a point. Hey, I got a point right here. So I'll just use point slope form, y minus y naught. It's tangent line formula in point slope form. Y minus y naught equals m, x minus x naught, where the y naught is root 2 and the x naught is 1. So the slope m is dy dx, so that's root 2 over 2. X minus root 2. Y minus root 2. Sorry, x naught is 1. So I'll fix that. All right. So x minus 1. And then I'll just add root 2 to both sides to get into my nice point slope, my slope intercept form. Y equals root 2 over 2x. Here I've got root 2 over 2 plus root 2 would be positive root 2 over 2. And there's the slope of my tangent line. Okay, great. Let's do one more example. I want to find a point on this curve, and I have no idea what this curve looks like, which has a horizontal tangent line. So again, this is all going to stem from, since I have information about the parametric equations, and I want to know about tangent line information, I'll just use this fact that dy dt is equal to dy dx, dx dt. Okay, and let's C, we want a horizontal tangent line. Of course, that means that the slope is 0, which means that dy dx is 0. Well, of course, that means it doesn't matter what dx dt is. That means that I want to know where dy dt is equal to 0. That's all that matters to me. So, let's see here. Oh, first of all, there is a typo here. It should be t is greater than 0. My apologies. So here is our problem. Dy dt is equal to 0. What is dy dt? Well, here's my y. So that's going to be the derivative with respect to t of t plus 1 over t. All right. And that gets me 1. This is t to the negative 1. So bring down that negative, t to the negative 2, which is 1 over t squared. All right, and I'll just, that tells me I want t is equal to, 1 is equal to 1 over t, so t squared must equal 1. So t is plus or minus 1. Now that I've corrected the typo here, the domain of this function, t couldn't equal 0 and be in the domain because of that over t thing here. But t is positive, which means I have to remove the extraneous solution. So it's just going to be plus 1. Okay, so what do I do with this information? T is equal to plus 1. Well, the problem says we want the point on the parametric curve. And I know that that t value must be 1, so all I have left to do is find x of 1, which is the natural log of 1, which is 0. Y of 1 is 1 plus 1 over 1, which is 2. So the point on the curve is 0, 2. And that is the point which has a horizontal tangent line.